Hi everyone, so we're going to talk about the last type of decrease and conquer algorithms. This one is the variable size decrease algorithms. So we've already seen Euclid's algorithm. So in general, what the idea behind this strategy is that it's the same deal as decrease and conquer, where you're trying to decrease to a smaller subset of the problem, solve it, and then apply it to the larger problem. And we looked at when you decrease, you can decrease by a constant factor, which we saw with 1. We decrease by half when binary and other binary search and other algorithms. In this one, you're going to be decreasing your problem size each time, but for variable parts. So you're not sure ahead of time, and it won't be consistent, the size that you decrease each time. So hopefully these will come across. And Euclid's is a really good example of this. So remember when we did Euclid's algorithm, we were finding the greatest common divisor, and we did that by iteratively using the calls to the GCD function, where we would look at n and m mod n until we got to that second argument to be 0, right? So every time you decrease your the number, but it's variable of how much it decreases. And if you look at this algorithm and you put together the recurrence, you'll find that this is at least it's every time it's cutting it in half. More than half, right? Because you're taking m mod n, so the remainder, so it can't be any more than half or any less than half. So you're cutting it in at least half each time. So you know that at least your runtime is going to be like binary search, where you cut it in half each time, and you will find that this is big O of log n. The next very important problem is the selection problem, and the idea here is that you want to find the kth smallest element in a list of numbers. So for instance, the median. So the median is the middle point in a set of numbers, and the set of numbers doesn't necessarily have to be sorted, and you want to be able to pick out what the median is. So the value that in a sorted list of numbers would be n divided by 2. And if that's an even set of numbers, then it would be the ceiling of n divided by 2. So median is really important. So we'll keep continuing with that. It's really important in statistics. So there's a bunch of different algorithms for the selection problem. The first way that you could think about doing it, the easy way is, I say easy to implement way is you first sort the algorithm or sort the array, and then you just walk through and you grab, or you don't even have to walk through because you have an array, so you can just grab out the kth element, and you know that is the element that you want. So for instance, you sort it and then you index n at n divided by 2, and you'll get the median. So again, this requires it to be sorted, and the fastest sorting algorithm that we haven't talked about it yet, is merge sort, and some other algorithms too, but the fastest you're ever going to get is n log n. That's the best efficiency you're ever going to get with a sorting algorithm this far. So your efficiency for that selection solution will be no better than n log n. However, there's a smarter way of doing it. A faster algorithm has been developed, and it's called array. It's based on array partitioning. And the idea here is that you can partition your array such that at this anchor element here, all of the elements to the left of it are greater than or less than it, and all of the elements to the right of it are greater than it. So, right? So if we assume this structure, when we are looking for our kth element, if k is equal to, if s is equal to k minus 1, let me see, why is this equal to, because we're indexing from 0, okay, fine. But basically, if s is equal to k, so you found your kth element, then you're done. If not, you know that, so if s is greater than k, then you know you're going to need to look for it here, right? All these are less than it. So if S is greater, then you need to look here. And if S is less, then you need to look in the partition to the right. So this partitioning becomes really important. All right. So a simple partitioning algorithm will do the following. So you will have a pivot, and you will look into your array, and you will start to swap things such that you move things that are less than it to a certain place, and things that are greater than it to a certain place. And so, for instance, these are not checked yet. These have the correct structure. These haven't been checked yet, and so you're kind of walking down through it. I'm going to skip this one because we're going to go into more depth on a different partitioning algorithm. So Lambuto, whatever, this partitioning algorithm is as follows. And it has a runtime of big O to the n. So this is better. It's much better than n log n. So the idea is here. So you take your pivot, usually you start R at the very end, and you start to partition your array such that you have the section at the beginning is anything that is less than it or equal to it, and then everything in this red partition is going to be greater than it. All right, so you can see how I and J are moving. I'm going to stop moving my mouse because it keeps doing that. But you can see how this is like in the middle of it where it's still kind of looking through things. Okay, so here is a full example. So we start at the beginning and we say 4 is our pivot. So in this algorithm, we always start at the end. And now we start to look at the rest of the array and we start to swap things. So for instance, we start with I is equal to the first one, and we compare it. So J first would be here at 8, and we'd compare it and we'd find, okay, we don't need to swap anything. But then when we compare, so then J moves on and we compare it to 2, we find 2 is less than 4, so that those need to be swapped, right? So we're trying to get this structure such that some n number here will be less than 4 and some n number here will be greater than 4, right? Okay, so when we do the swap, we end up like this, and so this blue is going to be the one partition that we know is less than 4, and these two red are going to be the partition that so far we know is greater than 4. So we continue, we start now with 8 I increments. So once we do our swap, I increments, because we already know 2 is in the right partition. So we go and we increment I into our greater than partition to look for any other numbers that we need to swap over. So here we look. These are all greater, but we do find a 1. So when we find the 1, that's when we're going to swap with 8, right? And so now we have this new partition. All of these we know we've already looked at when we compared to 8. We already looked at these and we know that they're all greater than 4, so we don't have to look at those again. So I moves, I does not move. Hold up. Did I say something wrong? No? Okay. Yeah. Go away. Little tooltip thing. All right. So now I moves 1 over. Okay. So we did, in this section, we did our swap with 1, and now we're here, and now we can move I over 1, and we start to do our comparison with 7. So 7 we already know is in the right partition, so we look and we compare this next one at J with 4, and since it's smaller than it, we're going to swap these two. And then finally, so we swap those and we have our partitions. So now I will move over one last time and we'll swap it with 4. And this will be how we finish. Right, so what we'll return as the pivot, or in our original nomenclature was S. So what we'll return as S is 4, and P and Q will just be beginning and end. So the way that this plugs into something kind of useful is this partitioning algorithm is used in quick select. So if you wrap this partitioning algorithm around another function, or you put it into another function, like a quick select, you can quickly select the kth value that you want. So you start with your partition and you get your first S. So this, we pass in the full array, and so we use the last element always as the anchor. And if perchance S equals to K, so here this would be, so it's a little, we'll index from 0 because we're computer scientists. What would return here is 0, 1, 2, 3. So 4, we know 4 is the third smallest element in this array, right? So if it so happened that we came here and the very last element in this array happened to be what K was, then we're done. If not, this is when we look and see, okay, is K greater than S, or do we need to go and look at the beginning of the array? So this is just cut off the beginning from 0 to S minus 1, where S was the past pivot, and we look for K again. Or do we need to look for it in the left, or on the right side, where it was greater than? And so here we pass at the end of the array, everything past the anchor to the end, the original anchor, and then we of course adjust our K, because our K now, since we have a smaller array, so we would just now be searching this array, we need to slightly adjust our K so that we're still looking for the right kth element. So that's how this is going to fit in. So quick select is, so make sure, if it didn't make sense to you, go through the slides again, go through the lecture again, because soon we're going to talk about quick sort, which is a really cool algorithm that takes advantage of this quick select. So notice here, as you're doing your partition, at least one of the elements ends up in the right place, and you have two sub arrays that aren't sorted, but they're in a relatively right place, meaning that they're, now you can just sort these three elements instead of sorting the entire thing, or you could sort these three or these four. So let it sink in, look back over it, let me know if you have any questions. This is the end of Decrease and Conquer. Please do your homework and let me know if you have any questions. Thanks.